Points in 3D space. Number 1, 3D coordinates. A point in 3D space is represented by three coordinates, the x, y, and z. X, y, and z, these coordinates specify the position of the point along three axes. Y-axis runs horizontally left to right. The y-axis runs vertically up to down, and for z-axis runs into the out of the screen, forward to backward. For example, the point 3, negative 2, 5, 3, negative 2 and 5 means 3 units along the x-y-axis will become right, and negative 2 units along the y-axis it means down, and 5 units along the z-axis for forward. Defining shapes. In 3D graphics, points are used to define the vertices of shape polygons. For instance, a cube has 8 vertices, each specified by its x, y, and z coordinates. These vertices are then connected by edges to form the surface of the cubes. Manipulating objects. Once points are defined, they can be manipulated to transform objects. Translation. Moving the object to a different location by adding a constant value to the coordinate of all its points. Rotation. Rotating the object around an axis, like turning a dice by changing the coordinates according to rotation matrix. Scaling, for we changing the size of the object by multiplying the coordinates by a scaling factor. Applications. Points in 3D space are used in various applications such as modeling, animation, rendering, and modeling, creating a 3D models of objects, characters, and environments. Animation, moving and transforming these models to create motions. Rendering, projecting these 3D points into 2D screen to produce an image, simulating depth and perspective. Coordinate system. Different coordinate system can be used depending on the context. Word coordinate, the global position in the scene. Object coordinates, the local position relative to the object of origins. Camera coordinates, the position as seen from the camera point of view. Vector for directions and movements. So what is vector? Think of a vector as an arrow pointing from one place to another. It has two important features. We have direction and magnitude. Direction, which way the arrow points, kung saan tuturo yung arrow, and magnitude, how long the arrow is, in other words, how far it goes, kung gaano siya malayo pupuntahan mo. Number 2, vector for directions. In a 3D world, vectors are used to describe directions. For example, if you're programming game and you want a character to walk forward, you use a vector point in the direction they should move. If the character needs to look up or down, you change the direction of the vector. For vectors for movement, vectors are also describe movement. Suppose you have a spaceship in a game that needs to fly forward. The vector tells you not only which direction to move, but also how far to move in that direction. If the spaceship needs to speed up, you increase the magnitudes of the vector. Combining vectors. You can combine vectors to create more complex movements. For example, if your characters need to move diagonally, you can combine a vector pointing right with another pointing up. The resulting vector points diagonally, and its length tell you how far to move. Scaling vectors. Scaling vectors changes its magnitude, how long the arrow is without changing its direction. This is like pressing a gas pedal. The direction of the car stays the same, but it speeds up in graphics. This helps in scaling movements, like making a character run instead of walk. Rotating vectors. Rotating a vector changes its direction while keeping its magnitude the same. This is like turning a steering wheel. The car turns but speed doesn't change. This is useful for changing the direction an object faces or moves. Practical example. Imagine you're programming a game where a character needs to follow a path. Vectors can be used to point from the character's current position to the next point on the path. By following the vectors, the character moves smoothly from point to point. Matrices for geometric data manipulation. What is matrix? A matrix is like a grid of numbers arranged in row and columns. In graphics, we often use 4 by 4 matrices, a 4 rows and 4 columns, because they can easily handle 3D transformations, including translation, rotation, scaling, and more. How matrices manipulate geometry. Matrices can transform points and objects in a 3D space in several ways. Here are the main types of transformation they perform. 1. Translation. Moving objects. Translation matrices move objects from one place to another. For instance, if you want to move a character in a game from point A to point B, you use a translation matrix to add specific values to the character's position coordinates, effectively shifting them. Rotation. Ito yung for turning objects. Rotation matrices turn objects around an axis. For example, to make a windmill spin, you apply a rotation matrix around its central axis. The axis changes the coordinates of each point of the windmill blades, making them rotate smoothly and natural. Scaling for resizing objects. Scaling matrices resize objects, either making them bigger or smaller. This is like zooming in or out an object. By manipulating the coordinate by certain factors, you can uniformly increase or decrease the size of an object. Shearing. Or shearing for slanting an object. Shearing matrices distort an object along one axis, creating a slanted effect. It's like taking a rectangle and pushing up the top side to the right or left while keeping the bottom side fixed.